In this video, we present our design of a reconfigurable robot leg. Unlike animals, robot legs have a large joint range of motion. However, only a small part of its joint space is used in operations. In this example of robot hiking, the leg only operates in a small section of joint space, and it falls on the right half of this plot. This happens because robot legs have symmetric kinematics and the two halves of the joint space are equivalent. In this work, we present a design that exploits this feature by creating an alternative mode of operation in the otherwise unused half of the joint space. Specifically, we engage a strong parallel spring using a passive clutch mechanism. In a spring-suspended configuration, the strong parallel elasticity would be able to support the weight of the robot leg passively without actuator efforts. This configuration could also improve the hopping performance of the robot leg due to the energy storage function of the parallel spring. Finally, the spring could always be disengaged by switching into the other configuration, such that the actuator does not need to compensate for the spring torque. This picture shows the design of our 2 degree of freedom planar leg prototype. The size of the leg is small and it only weighs 830 grams. It is worth mentioning that the clutch mechanism and the spring only contribute less than 40 grams of the total weight. The design of the spring and clutch mechanism is shown in this plot, and we selected the spring constant and engagement point, taking into consideration the passive stance ability, the energy storage capacity, as well as the maximum actuator torque after compensating for the spring. This video shows how the clutch mechanism works. In one half of the knee joint range of motion, the joint and the spring are disconnected, while in the other half the joint motion pulls the linear spring, so equivalently, a parallel spring acts on the knee joint. We first evaluated the performance of our design in the stance tests, in which we commanded the leg to stand at different base heights in both configurations, and measure the motor torque required on the knee joint in a steady phase. Initially, we observed that the parallel spring, when engaged, reduces the torque demand when the base height is higher, and drastically increases the torque demand when the base height is low due to the required torque to actively pull the spring. When we perform the same test again with 250 grams of payload, however, the situation is different, and in most cases, the torque demand is lower in the spring-suspended configuration. Finally, we tested the hopping performance of both configurations. We implemented virtual model control and tuned the parameters such that the leg hops to the same base height in both configurations, as demonstrated in this video. From the data collected, we observed a huge reduction in both peak actuator torque and the energy consumption per hop. In summary, we have developed a prototype of a reconfigurable robot leg that uses a passive and lightweight clutch mechanism to control the engagement of a parallel elasticity. The parallel elasticity, when engaged, passively supports the weight of the leg even with additional payload, and it improves the hopping performance. While in the other configuration, the parallel elasticity is disengaged to avoid actuator working against the spring. Thank you for your attention.